The Avogadro constant and the mole. So the definition of a mole, 1 mole, which we use the symbol MOL, of a substance contains 6.022141199 times 10 to the power of 23. The only one we're going to worry about when we're doing our calculations is just going to be 6.02. Don't worry about that part. So 6.02 times 10 to the power of 23. And it represents how many particles in a substance. Okay? But now, that number is really large. Okay? So we don't really use that when really describing a lot of things. Right? And I'm going to show you in a sec what that means and how we try to simplify it. This value is called the Avogadro constant. We're going to use the letter N, subscript A, capital A. Okay, so the mole is defined as the amount of substance that contains as many elementary entities, so atoms, molecules, formula units. I'll talk a little bit about what a formula units are in just a second, as exactly 12 grams of carbon-12. Remember we talked way back about how a lot of the calculations are all based on the isotope of carbon. Okay, so as we said, remember that pretty much the masses that we've calculated when we looked at the different types of isotopes for each atom, they were all related to that of carbon. Okay, carbon-12 specifically. So what does this all mean? Okay, so if we have 1 mole of carbon, we have 6.02 times 10 to the power of 3 atoms of just carbon. But if we're looking at 1 mole of sodium chloride, we have 6.02 times 10 to the power of 23 formula units of sodium chloride. And here's that formula units that we're talking about. When we're looking at something that is ionic, ionic meaning metal, non-metal, we never really have 1 molecule of NaCl. What we have is, because they both carry charges, we have pretty much a string of NaCls. Okay. And then connected to this Na is Cl, NaCl, Na. Okay? And there's that connection between. So when we're talking about sodium chloride, we never really look at it as 1 molecule of sodium chloride. We look at it as formula units. Okay. Now, if we're looking at it in terms of a molecule, so 1 mole of hydrofluoric acid is equivalent to 6.02 times 10 to the power of 23 molecules of HF. So if we're talking about 1 mole of water, let's say, as another example. Okay. So 1 mole of water, okay, water being an actual compound, an actual molecule, we're looking at it having 6.0 times 2 times 10, to the power of 23 molecules. Okay? That big. 6.0 times 10 to the power of 23. Oh, if you're looking at let's say a whole piece of gold, let's say, a bar of gold, within that, you're going to have so many. It all depends on how many, let's say, atoms of gold is, let's say, within that piece that you have. Right? So we look at it as something very, very small in order to be able to fit so many. Okay. So any type of item that you have that you're going to see, but a number like this is just really not feasible to talk about. Right? We're not going to come around and go, well, I've got, 6.02 times 10 to the power of something, atoms within this bar of gold. Or in this glass of water, I've got 6.02 times 10 to the power of. So what we use is a smaller unit called a mole to kind of explain how many of these particles we actually have in our confined space. So, how many atoms are in 2 moles of aluminum? Okay. So, we know that we have 2 moles. Okay. of aluminum. We know that 1 mole of aluminum, 1 mole has how many atoms? 6.02 times 10. 23. Good. So we have 1 mole has this many, but we're talking about atoms, and we're looking at 1 atom, right? Which atom is it? Aluminum. So now, this we can rewrite it as, well, we have 6.02, atoms. So in other words, we can rewrite this as 6.02 times 10 to the power of 23 atoms per 1 mole. Or we can look at it as 1 mole, okay, has 6.02 times 10 to the power of 23 atoms. So we can look at it as one of these 2 ways. Now, if we start off with this, which one of these 2, and they're both the same, they're just inverted, which one of these 2 can I use that will allow me, well, I start off with 2 moles. I want to cancel out 2 moles. And remember when we were talking about conversions way back last year, we were talking about what can I multiply that will allow me, so where will moles be put, top or bottom, to cancel out? Bottom, right? So which one of these? First or second? First one, right? Because moles are here at the bottom. So in 1 mole, it's equivalent to 6.02 times 10 to the power of 23 atoms. So now moles cancel out. So mole. What am I left with? What units am I left with? Atoms, right? So to do that, now I just multiply 6.02 times 10 to the power of 3 times 2. So I could do that. We can do that a lot simpler than I did it there. Okay? But the reason why I'm showing it to you this way is because this way, okay, if you understand the concept of canceling out units, okay, it'll help you figure out what step to go. Am I going to multiply? Am I going to divide? Right? This way, you don't have to worry about it. This way, you can just follow along as we're multiplying by a set of fractions, and then figuring out which order will our set of fractions be. So when we multiply 2 times 6.02 times 10 to the power of 23, what do we get?
Is it okay if we got another exponent?
Yeah, well, because we're multiplying this thing really twice by 2.
Yeah, I got 1.204
times 10 power of 24, and so that represents what units though? Atoms. So in 2 moles of aluminum, so if we had aluminum, okay, and we were trying to isolate 2 moles of it, we would have an equivalent of this many atoms. But now, what are the least number of significant digits in my question? One significant digit. So, this is the one we need. So my answer is 1 times 10 to the power of 24 atoms. Okay? So, we haven't talked about significant digits in a while. Please make sure you remember them.
Oh.
Exactly. Exactly.
Why
So,
do you have to use the word mole?
because we don't want to use 6.02 times.
No, why do you use the word mole? It's like, I think of the question and everything. Oh, because...
Well, have you seen the worksheet that I posted? You'll see a mole in it. I'll tell you a little more about that later. Now, converting moles to number of particles. What we've done is we take the number of moles, right, like we had in that example, 2 moles, and all we did was multiply it by 6.02 times 10. Sorry, 6.02 times 10 to the power of 23 to get the number of particles. Now, we were looking at atoms. Okay, if we are looking at it in terms of molecules, 1 molecule, okay, is equivalent to, let's say, that many. So, sorry, 1 mole is equivalent to that many molecules. Okay, so we're using it to pretty much count atoms. So we're counting atoms, molecules, formula units. Formula units, again, like I said, ionic. Relationship between moles, number of particles, And the Avogadro constant is as follows. So we're going to use the following letters. Capital N, number of particles. Lowercase n, number of moles. As we said already, the n with the subscript A represents the Avogadro constant. That's 6.02 times 10 to the power of 23. Okay? And there is the formula that we use. Okay? And this is only to find the number of particles. Okay? Which means if we wanted to find the number of moles, we'd have to isolate for number of moles by moving this over to that side of the equal sign. All right? And obviously, we don't really need to find that because the Avogadro constant is 6.02 times 10 to the power of 23. So we know that the variation, so if we needed to find number of moles, we isolate for n, okay, and we get the number of particles divided by the Avogadro constant, if we were trying to find the number of moles of something.
Also, just need this equation.
You use this equation, right? So we can simplify what I've already showed you, okay? Or you can use my rule for what they call factor labeling, okay?
So we have to memorize this equation.
Well, see, you can either memorize this equation or know about the rule for canceling, right? Remember how we canceled mole and mole, right? So if you know how to do that, you won't really need to worry about the formula, okay? How many atoms are found in 0.25 mole of potassium? Okay, so really simple, similar to what we're looking at, but what are we? But we're looking at potassium, so we're looking at just the atom itself, right? So, in reality now, we don't have a full mole, we have less than that. Okay. So, we start off, we want to find out the number of atoms, so the number of moles, Avogadro number. Now, here it is, the way I wanted to show it to you guys at the beginning. So we have 0.25 mole, okay, of potassium. But now, we know that in 1 mole is equivalent to 6.02 times 10 to the power of 23 atoms. Or 6.02 times 10 to the power of 23 atoms is equivalent to 1 mole. They're both the same. But we are going to multiply this by one of these, either this or that, based on which one will allow me to cancel out mole. Which one will allow me to cancel out mole? First one or the second one? The second one. So, mole, what we were trying to do, let me show you in a different color. Mole, we're trying to cancel out. So all we're doing, just like the equation showed us, we take the number and we multiply it by 6.02 times 10 to the power of 23. Okay. And that's what we end up doing there. And there's my answer. Okay. So once you've multiplied all this together, that's what you get in terms of the number of atoms of potassium. Okay, 1.51 times 10 to the power of 23. But now, what are the least number of significant digits of my question? 2. So my answer must be simplified to just 2. 1.5 times 10 to the power of 23. And don't just leave the number, right? Remember, units, right? So the units are atoms of potassium. Okay, next one. How many atoms are in 1.25 mole of water? How many atoms are in 1.25 mole of water? So, we know we have 1.25 mole water. Okay, so we're going to multiply it by, for me to cancel out moles, where must moles be? The bottom. The only thing is mole, okay, is this water here an atom? No, it's a molecule. So technically we're looking at 1 mole is equivalent to 6.02 times 10 to the power of 23, not atoms, but molecules. Okay, so we're looking at molecules. So now we are going to get how many molecules are in 1.25 moles. Okay, so our answer, when we've canceled out mole, will give us molecules. But we're trying to find out atoms. Right? We're trying to find out atoms. How many atoms are there in 1 molecule of water? Which are they?
Hydrogen.
How many? 2 hydrogen, 1 oxygen. Okay, so there's a total of 3 atoms in total. So what we're going to do is, let's find this result first.
Divided by 3.
Okay, we'll watch what happens. So we're going to multiply those 2, and we're going to get the number of molecules, not the number of atoms. Before we did it, because we were talking about potassium, we were talking about, specifically aluminum. Okay, but now we're actually looking at an actual molecule. Okay, so when we multiply that, so we're looking at molecule because water is a molecule. Okay, it's not an atom. We have atoms within that make up this molecule. Okay, so when we calculate it, we get the following: 7.53 times 10 to the power of 23 molecules of water. So 0.53 times 10 power of 23 molecules, okay, of water. Now we're going to multiply it by something. But now I don't want my molecules units, right? This is where we're talking about the factor labeling, trying to cancel out. So we are always multiplying it, let's say, by a fraction. I want to do this. So what word should I put down here? Molecule, right? But now, in 1 molecule, let's get rid of that S. In 1 molecule, how many atoms are there? 3. So there are 3 atoms in 1 molecule because we're referring to here water.
So this is bigger than say when H3O, then there'd be 4.
It'd be 4 atoms, exactly. You could have a formula that could be something like, let's say, phosphoric acid. And then you're going to have to break, you're going to have to kind of do the same thing, but it won't be 3 atoms in 1 molecule. It'll be, 8 molecules in atoms in 1 molecule. So what we're going to do is then we're going to take these out, and now my molecules here cancel out. What am I left with? What units? Atoms. So I know that if I have this many, molecules, but that 1 molecule is made up of 3 atoms, I'm going to have 3 times the amount of atoms as that, because in 1 molecule I have 3 of them. So we're going to multiply this by 3, and we get 2.26 times 10 to the power of 24 atoms in 1.25 moles of water. Okay? And again, same thing. We have how many significant digits in my question? The least number? 3. And my answer also shows 3 significant digits. So let's look at how many molecules are found in 0.65 mole of potassium nitrate. Okay? Similar to what we've already done. Okay? Now, here's the thing. Remember what I said at the beginning? I said the stuff that we've needed to know up until now, you need to know naming. Don't forget it. You're naming of it, because if you can't put together potassium nitrate, then that's it. You're losing marks. Okay? You're losing marks. So, we know what? We know we have 0.65 mole of potassium nitrate. What is the formula for potassium nitrate? KNO3. Good. See, not so bad. But now, we don't want mole, right? So for me to cancel it out, where am I going to put mole? Top, the bottom, right? Mole. So in 1 mole, how many atoms do we have? But now, are we looking at atoms or molecules? Molecules, because we're looking at a whole molecule of that. So in 1 mole, we have 6.02 times 10 power of 23. And it's not atoms like the other one, it's molecules. So still, 1 mole is equivalent to 6.02 times 10 to the power of 23 atoms. 1 mole is equal to 6.02 times 10 to the power of 23 molecules. And 1 mole can be equal to 6.02 times 10 to the power of 23 formula units, ionic compounds. Okay? So, now, my moles cancel out, and all I'm doing is multiplying my moles by that. But my answer will give me in... Okay. So my answer will give me 3.91 times 10 to the power of 23 molecules of KNO3. And what's the question asking for, though? Atoms or molecules? Molecules.
Oh.
So we stop there.
Okay.
But if we were asked to find atoms, how many atoms are there in KNO3?
4 or 5.
There are 5, right? So 5 atoms in 1 molecule. Oh my goodness, I can't even spell that. Right, but now, what are the least number of significant digits of my question? 2, right? So I need the 3.9. All right, we look at the 1 after it. Does it change?
No.
No. So the answer is 3.9 times 10 to the power of 23 molecules. This time I can do it. Molecules of KNO3.
Does it get harder?
I don't know, it depends who you're asking. You're asking me or maybe someone in this class. Right? See, because to me, I look at it and go, oh my goodness, I'm giving away marks every time I put together a test. Right? Because I don't really go out to try to trick you. But somehow they become tricky. Right? They become tricky. Okay.
Do you always want us to switch it to atoms?
Pardon? Well, it depends.
Right now.
Look at it. So right now we're asking how many atoms are found in 2.25 mole of silicon. Silicon, molecule, formula unit, or atom?
Adam.
Atom.
I have a question.
Yes.
How do you count atoms?
Hmm?
Or like before the question?
Couple on your fingers.
Why?
With this one?
Yeah.
Well, we're asked for molecules, but if the question said for atoms, we would take this answer, right? And we multiply it by something that will allow me to cancel out molecules. So where am I going to put molecules? The bottom. Right? Molecule. But in 1 molecule, we're going to have how many atoms? 3, right? 3 oxygen, 1 nitrogen, 1 potassium. 3 plus 1 plus 1? 5. So there are 5 atoms in 1 molecule of potassium nitrate. Right? Because you're making your reference to potassium nitrate. So then we would take this answer and we'd multiply it by 5. If we were trying to, if this question was not how many molecules, but how many atoms. Okay? Oh, good question. Okay, so let's go back to the one I just kind of gave. Okay. So, same thing, right? We start off 2.25 mole of silicon. All right. And same thing, we're just multiplying it by 6.02 times 10 to the power of 23. But we're looking for atoms, so it just stays as atoms. Okay. Notice here, my moles cancel out. My answer is going to be in atoms. Is that what I want? Yes, because I have silicon. Silicon's an atom. Okay. Is my answer the right number of significant digits? Yes, 3 significant digits. How many atoms are found in 5.25 mole of strontium phosphate? Okay, take a minute. So, someone give me the formula for strontium phosphate. SR3 PO4. Good. So we know that we have in one molecule of this, right? We have how many atoms? Pardon? Oh, sorry. Sorry. So so in one molecule now, this is going to change the next part. In one molecule, how many atoms are there? How many? 13. So we know 13 atoms. Okay. 13 atoms. Now, we're starting off with 5.25 mole, right? So, 5.25 mole, okay, of strontium phosphate. I don't want mole here. I don't want mole. So for me to do that, where am I going to put mole? The bottom. In 1 mole, I have how many molecules? We're looking at a molecule here. 6.02 times 10 to the power of 23. So we either have molecules, atoms, formula units. One of those 3. And it's always going to be based on, this is always based on what you have in your question. Okay? Because they're interchangeable. So now, when I do cancel mole out, okay, when I multiply these 2 together, I get my answer, but the answer will be in molecules, right? So it came out to 3.16 times 10 to the power of 24 molecules. But I want atoms. So we have 3.16 times 10 to the power of 24 molecules. Molecules. My goodness, for some reason today I cannot spell molecules. I want to cancel molecules out. Where am I going to put molecules? Right? So we look at that. But we're looking at 1 molecule. We want to turn it into atoms. So in 1 molecule we have 13 atoms. So we're going to multiply these 2 together. And there's no point to the dividing by 1, because anything divided by 1 stays the same. Okay. So, molecules cancel out. My units will be in atoms. So my answer comes out to 4.11 times 10 to the power of 25 atoms of strontium phosphate. How many moles are found in 5.35 times 10 to the power of 22 molecules or formula units of NaCl? And so here's where the whole notion of factor labeling comes into play, and why I've been using that whole times a set of fractions. So we have 5.35 times 10 to the power of 22 molecules, okay, of NaCl. So we want to cancel out molecules. We don't want those units. So we're going to put molecules here at the bottom. And so now we're going to cancel out molecules. And we know that we have 6.02 times 10 to the power of 23 molecules in 1 mole of something. Because we're being asked to find how many moles. So we're going backwards now. We're going in the opposite direction to get what we're looking for. Right? So, in actuality, what we're doing is really we're just dividing this by that, according to the way I showed you guys the formula. Okay? Or you can use the factor labeling method to be able to cancel things out. So we're going to multiply 5.35 times 10 to the power of 22 by 1. and then divide it by 6.02 times 10 to the power of 23. Okay? And we end up getting 0.089 mole of NaCl. So we have 3 significant digits in our question. So we should simplify our answer to 0.0890 mole of NaCl. Okay, notice here, 1, 2. This 0 we don't need, but we've made it significant by adding it. Okay, because it is after the decimal. So, next question. How many moles are found in 6.39 times 10 to the power of 22 atoms of carbon? Okay, so we know that because we're going from moles, okay, using atoms, okay, we can either go 6.39 times 10 to the power of 22 divided by 6.02 times 10 to the power of 23, okay, or we can start off with atoms. We want to cancel out atoms. So we know that we have 6.02 times 10 to the power of 23 atoms in 1 mole. Okay? So we can use it in one of these 2 ways, and we get the following answer. 0.106 moles of carbon atoms.